Okay, so chapter 6. So two forms of energy, kinetic energy and potential energy. You should know what each of these are. And the reason we concern ourselves with biology and these types of energy is what we do is we convert one to the other. For example, humans, when we eat something, right, we're going to have a form of potential energy in the form of chemical energy. We're going to convert that to ATP, and that ATP then can be used to drive processes, cause motion, your muscles to move, form of kinetic energy. First law of thermodynamics says that energy cannot be created or destroyed. Okay? Total energy that enters into a reaction equals the total energy that comes out of the reaction. Now, this is not to say that all of it's going to be useful. Okay? Many times it's not. Okay? But all we're saying here is that the total energy, if you added up everything that came out of a transfer, compared it to before, they would equal. Okay? But here's the problem. What comes out is probably not going to be the same quality that goes in, depending on the situation. For example, gasoline, right? Gasoline's high quality energy. That goes in your engine. You burn the gasoline, you're going to get what? Kinetic energy. Your car is going to move. But if I looked at the kinetic energy of your car's motion and compared it with the potential energy of the gasoline before it was burned, would it be the same? No, it would not. Okay? You're going to have other forms of energy there. Heat energy. Feel the engine, it's hot. Sound energy. You hear the motor running. That sound energy. Are those energies going to kinetic energy? Energy of motion, moving your vehicle? No, it is not. Okay. Second law of thermodynamics. Energy flows from high-quality forms to low-quality forms spontaneously. Okay, before we said there's high-quality energy, low-quality energy, and going from high quality, such as gasoline, to the lower quality forms happens spontaneously. Energy flow. Key point here is what? All energy is going to come ultimately from the sun. One little exception to that we mentioned in class was nuclear power. Barring that, all energy on Earth comes from the sun. Okay? What pathway is it going to follow? Well, that energy is going to go from the sun to producers. Okay, the producers are plants. And then we're going to consume the producers, either directly or indirectly. Okay, for example, you might eat a fruit or vegetable that you are directly consuming a producer. You could eat a cow. You could eat a hamburger. Well, that cow digested plant material, and then you digest the cow. So you're indirectly getting your energy from the producer, which is the plant. Okay. So know what the energy flow is. It goes from producers to consumers. And we see there's a cycling there, right? See how some things come out of the producers and then goes to consumers? It's a cyclic thing. It says nutrient cycling. What that means is that what the producers release, we use. And what we release, the consumers, the producers use. Now, going back to the laws of thermodynamics, when we do a conversion from, say, gasoline to motion, that transfer, there's always going to be some type of loss of energy. Now, it's not lost as in goes away, it's just lost in terms of usefulness. Okay? Think of that engine example, right? We take gasoline and we burn it, cause kinetic energy. At the other end, we get motion. But then the motion is useful, but the heat energy, the sound energy is not useful. Okay, energy conversion, transfer, loss. Okay, the point is this, that we have said in the past that when we do an energy transfer, it's not 100%, right? We have useful energy before the transfer. After the transfer, we have some useful energy. But if we compare the energy after that's useful to before that's useful, they're not the same. It's always going to be that what comes before is always going to be more energy than comes after. Okay, this is important in biology because we look at these trophic levels, these levels of organization between the producers and the consumers. And what we see is that as we transfer useful energy between these different levels, we have a loss of about 10% at those conversions. So, good example here, that last point. The sun to the plant, okay? The sun's going to give 1,000 calories of energy to the plant. But the plant's only going to be able to convert 500 calories of that into plant material that can be useful to consumers, such as a cow. Okay? The other 500 calories lost with heat, lost with other cellular reactions, not directly making a compact, useful form of energy. Okay? Plant goes to a cow. The cow digests that 500 calories of plant material. Well, the cow's got to live, right? The cow's going to take that material and bacteria is going to work on it, and the cow's going to move around, so on and so forth, and it's only going to be able to make 500 calories of meat as a result of the 500 calories of plant material that went in. So 500 calories of plant material go in, and only 50 calories of meat that can go to the next level come out the other end. There's been about a 10% transfer between what went in and what came out. Okay, we eat a hamburger, have 50 calories of meat. We only get maybe 5 calories of useful work out of that 50 calories of meat. Okay, again, we have got to move. There's a loss in that transfer. End of the story is what? We get far less calories at the end of the process than went into it initially. Okay, and this is a cumulative loss. Every time there's a transfer, there's a cumulative loss of energy. Okay, so chemical reactions. You should know what a chemical reaction is, what a reactant is, and what a product is. Now we see this image and it says nothing of the rate, how fast this happens. It just shows us that it is happening. Enzymes are usually proteins, sometimes RNA, but these are going to speed this reaction up. Okay, this shows the reaction's happening, but does this happen one time a minute, a million times a second, one time an hour? It does not say. It only shows that it's happening. Enzymes will speed that process up. Okay, in this picture here, reactants to products, then the presence of an appropriate enzyme, this will happen many more times than it would happen alone. Why is that? Well, think of enzymes as catcher's mitts, right? It's going to grapple onto one molecule we call a substrate or two substrates, and it's going to get them in close association. And when they're close by, then they can form a bond or transfer bonds. We'll talk about what they do later on. But it's going to grapple onto these, and it's going to bring them in and do a function. Okay, that's the secret of an enzyme. Also, you should know that enzymes only speed up a reaction rate. They don't make reactions happen. They only speed the rate up. You should also know what exergonic and endergonic is. Endergonic means that energy goes into endergonic, and exergonic means that energy is released. And biology is all about endergonic and exergonic reactions. Okay, so ATP. ATP is the energy currency of the cell. Okay, I like to use the analogy of a $20 bill versus a $1,000 bill, right? Glucose is like a $1,000 bill. Why is that useful? Well, if you want to store a lot of energy in a compact form, $1,000 bill is good. or I should say glucose is good. If you want to store a lot of money in a compact form, a $1,000 bill is good. Okay? But then you have to ask yourself, is this a useful way of storing energy or money? Well, it depends on what you're doing, right? If you want to go to a store, if you want to go to Walmart, if you want to go to some place to eat, are they going to take $1,000 bills? Well, the answer to that is no. So the cell has to take that energy storage form, glucose, take it to the mitochondria, and do a conversion to make a stack of $20 bills. In this case, multiple ATP molecules. Okay, $20 bill is good, right? How is it good? It's useful in that you can use it in multiple places. It's accepted everywhere, right? Well, ATP is like that. It's accepted everywhere there's a need for energy. Just like $20 bills are accepted everywhere there's a need for money. But how is it not useful? Well, if you want to store a lot of energy, do you want to store it as a lot of ATP? Probably not. Just like if I want to store a lot of money, I'm not going to store it as $20 bills because it's just too big. It's too bulky. It's too cumbersome. Okay? So the idea is this, bottom line. The cell has forms of energy. Glucose, ATP. Glucose is a storage of a lot of energy in a compact form, has a lot more energy, like a $1,000 bill. ATP is a multi-use small unit of energy, just like a $20 bill is a multi-use small unit of currency. And we're going to concern ourselves with the formation of how we go from, not this chapter, but in next few chapters, how we go from this glucose molecule, do the exchange, and make the ATP molecules. So ATP, adenine triphosphate, looks like a base, right? Looks like a DNA base, has 3 phosphates. That last phosphate is the magic phosphate. That is the one with all the energy. Okay, when we put that last phosphate on, we have an energy carrier. When we remove that phosphate, we then transfer energy. Phosphorylation is putting a phosphate onto ADP. Dephosphorylation is removing a phosphate from ATP. Enzymes and substrate and products. What you should know with enzymes is the following terms. What an substrate is. A substrate is what goes into an enzyme. Okay. Enzymes are mostly made of protein. You should know that. Sometimes RNA can be involved, but mostly enzymes are going to be protein. 3, enzymes are not used up in a reaction. Okay. Over time, yeah, they can, wear down over millions of reactions, but we consider them not to be used up in a reaction. Okay. And enzymes are going to make a reaction happen many times faster. The reaction rate of a chemical reaction increases due to an enzyme. Another term you should be familiar with is an active site. And also the idea of active site to substrate agreement. So what do I mean by that? So looking on the left, we have it looks like a piece of corn almost, right? And substrate active site. See that? And the substrate has an S shape and there's an active site. Okay. That kind of implies that the substrate fits in the active site, kind of like a lock and a key, right? Well, it is kind of like that. That an enzyme is specific to a type of substrate. Okay, not one enzyme will only work on one or a limited number of substrate molecules. There's specificity there. Enzymes are not multifunction, multi-purpose. Now the diagram on the left shows a more accurate representation of the substrate versus the active site, how it looks. Okay, the active site is small. The substrate is very small compared to the entirety of the enzyme. But that idea of specificity where the substrate and the active site have an agreement, have almost like a lock and a key type of relationship is still there. So enzymes are specific to only one or a limited number of substrates. They are not multitaskers. They're not multifunction molecules. They're only going to grapple onto, hold on to a few numbers, usually one substrate. The active site is going to be complementary in shape, polarity to that substrate. It's almost, think of a catcher's mitt and a baseball, right? How they're complementary. One holds on to the other. So that might be a way to think about it. The active site is like a catcher's mitt. The substrate is like a baseball, and they just fit nice and snug into each other. How an enzyme works. You have functional group transfers. We talked about all these in class. A rearrangement, condensation, and a cleavage. You can read that. But we talked about that in detail in class and actually drew something on the board about that. How enzymes work, and this is the secret of them, is they help substrates get together. Okay, and they orientate those substrates and the active site in such a way that they will react rapidly. Three things that affect enzymes are temperature, pH, and salt. Okay, and we're going to look at each one of these. Key point is what? As we change these conditions, the rate at which an enzyme will function will change. Okay. For temperature, right, enzymes are protein. And as you change the temperature, you're going to change the shape of the enzyme. So, control over enzymes. There has to be some type of control of enzymes, right? They're very powerful biological molecules. We can't let them just go do what they want to at the maximum speed possible. We have to regulate how they function. Okay. Two ways we can control this is allosteric control and feedback control. Two types of allosteric control. One on the left is an allosteric activator. So it looks like kind of like a Death Star. See, on the left we have a circular green object, has a Death Star look to it, right? And has that cup on its right. And we have that magnet. That's an allosteric activator. Without an activator, right, the substrate cannot bind to the active site of the enzyme. If that active site cannot bind to the substrate, well, it can't work on the substrate, and therefore that enzyme cannot work. But if there's an allosteric activator present, okay, that's going to be like something that will turn it on, right? As that allosteric activator enters into the enzyme, our enzyme active site opens up, it changes a little bit and allows our substrate to bind to the active site and allows the enzyme to function. Okay. An allosteric inhibitor is the reverse. Without an allosteric inhibitor, that enzyme will function correctly. But when an allosteric inhibitor is present, the enzyme cannot function. Okay? So you can either have something that will activate an enzyme from an inactive state, or something that will turn off an enzyme from its active state. Okay. Another feedback control is, feedback control. The idea here is that the product of an enzymatic reaction can be the substrate for another enzyme. Here it shows that the product of an enzyme will be the substrate of enzyme 2, and the product of enzyme 2 will be the substrate of enzyme 3, and then the product of enzyme 3 is the substrate for enzyme 4. But what happens is that the product of a later enzyme can loop back and turn off the process. Now I had a picture of this on the board, and we talked about it kind of in detail, but the idea is that the product of an enzyme down the road can loop back and turn off that initial enzyme. So shown in this image, enzyme 5's product came back and turned off enzyme 1. Now how is this feedback? What happens is this: because enzyme 1 turns off, the rest of the enzymes do not have substrate. Therefore, what is stopping or inhibiting enzyme 1 then goes away, and enzyme 1 can restart back up. So it's this undulating up, down type of activity, where enzyme 1 will function, the product of enzyme 1 after multiple enzymatic reactions will come back and turn enzyme 1 off. Because that reaction stops, that inhibitor then goes away, and enzyme 1 starts back up, and it starts making its products. In which case the same thing happens. That end product loops back and turns off enzyme 1. But that is feedback control. Okay? The product of a multiple step of reactions can loop back or come back and affect the initial reaction that makes it, or a step in the process. Redox reactions. You should know what a redox reaction is, what reduction is, and what oxidation is. Be aware that reduction is the adding of an electron. Very easy to confuse that. You think reduce and adding, it kind of is counterintuitive, but that's what it is. You're actually reducing the charge, and electrons have a negative charge, hence reduction or reduced. But you should know what an oxidative reduction reaction is. We take an electron from one, put it on the other. Okay, that's an oxidation reduction reaction. Reduction is the adding of an electron. Reduced is what has those electrons added. Oxidized is what donates or the electrons removed from. Very important in the electron transport chain. And this is a good summary slide of what a reactant, product, and enzyme is. We talked about these. Might want to review those points.